Here we're asked to compute the line integral over c of f dot dr by first finding a potential function f such that del f is equal to the vector field f that we are given, that vector field being f of xy is equal to the quantity of 3 plus 2xy squared times I plus 2x squared yj. The curve that we're talking about is y equals 1 over x from 1, 1 to 4, 1/4. Due to the nature of these directions, just find the potential function. We can assume that f is conservative. But suppose we didn't know that. We should find out, generally speaking, if we don't already know, is a vector field that we're looking at conservative? That is to say, is it true that the I component is the partial with respect to x of some function f? And is it true that the j component is the partial with respect to y of some function f? And remember, the tool that we can use to check that is if I take the partial of p with respect to y, is that equal to the partial of q with respect to x, considering the I component to be p and the j component to be q. So since p is equal to 3 plus 2xy squared, the partial of p with respect to y is equal to 4xy. And remember, what we're basing this off of is if p is a partial with respect to x, then what we have just done is created a second partial of f now with respect to y. And so it's a mixed second partial. Then the partial of q, if q is 2x squared y, the partial of q with respect to x is going to be 4xy. Since these match, we have that f is conservative. And that means that f is composed of an x coordinate, or an I component, I should say, that is a partial with respect to x, and a j component that is a partial with respect to y. And again, that check wasn't necessary for this particular problem, but it is for others in this section, and it's good form. So, since p is a partial with respect to x, it would follow that the potential function f of xy is equal to the integral of p with respect to x. And f of xy should be the integral of q with respect to y. Let's start with the first statement. The potential function f of xy should then be the integral of 3 minus 2xy squared, nope, that's plus 3 plus 2xy squared with respect to x. And so that's going to be 3x plus x squared y squared plus a constant, but folks, that constant is only constant with respect to x. What we just effectively did was we partially integrated. And so the constant could still depend on y. So we say the answer here is that f of x, y, the potential function, is equal to 3x plus x squared y squared plus g of y. Now I'm going to show you the technique that our author uses to recover basically what g of y is. What he says is, well, q now is the partial of f with respect to y. And so if I then take what we just got and differentiate it, partially differentiate it with respect to y, then first I'll have 2x squared y plus g prime of y, because we differentiated with respect to y after all, and so g of y differentiates to g prime of y. What we then do is we compare what we just wrote down with what we know q to be, and we see that q was given to be 2x squared y. Since what we have is 2x squared y plus g prime of y, we know that g prime of y must be 0. Therefore, knowing that g prime of y is 0, we can say f of xy is equal to 3x plus x squared y squared plus the integral of 0 with respect to y. And folks, that's going to be a constant. Now we were asked to find this potential function, so I'll circle it. That's how our author does it. The other way to do it is, I think, a little more direct. We can go back up to our f of xy is equal to the integral of q dy. And just so you have kind of a reference here, we would do this part here just after we have found the integral with respect to x of p. So we have here f of xy equals 3x plus x squared y squared plus g of y. Then we go to this other one, the integral of q dy. Now, since q is equal to 2x squared y, we are looking at f of xy is equal to the integral of 2x squared y dy. And that gives us x squared y squared plus some function h of x. You see, we, again, partially integrated, but this time with respect to y. And then at this point, I compare f of xy from integrating with respect to x, and then f of xy from integrating with respect to y. And since f of xy is equal to x squared y squared plus some function of x, but also 3x plus x squared y squared plus potentially some function of y, I see that the function of x must be 3x. You see, that's the thing that's missing between the two. So this is just kind of bookkeeping, roll call. So I'd put this together and say 3x plus x squared plus y squared. And then we don't have any function of y. We would say that that is 0. H of x has already been accounted for, but after the integration, right, there's still a constant. Take your pick between those two techniques. Either partially integrate and then partially differentiate, or partially integrate with respect to x and then partially integrate with respect to y. Well, now that we have our potential function, we can evaluate the line integral over c of f dot dr. And since we have a potential function, we know that the line integral over c of f dot dr is equal to the potential function f evaluated at x2, y2 minus potential function of f evaluated at x1, y1. In this case, remember that x2, y2 is equal to 4, 1/4, and x1, y1 is equal to 1, 1. So I've got 3 times 4 plus 4 squared times 1/4 squared. That's what I get when I evaluate the potential function f at 4, 1/4. Subtract off the quantity of 3 times 1 plus 1 squared times 1 squared, the values that we get when we evaluate the potential function at the point 1, 1. The result is 9.